Okay, it's 10 Pacific time, seminar time. Good morning, good afternoon, and good evening, depending on your time zone. Welcome to the CARB Research Seminar, Remote Sensing Measurements of Light-Duty Vehicle Emissions at Multiple California Locations. And this is for CARB Research Contract 20RD001. My name is Tao Zhan. I'm with CARB Research Division. I'm the contract manager for this project. Before we get started, I have a few logistics notice to make. The seminar is being recorded, and all the attendees will be muted during the presentation. For a more streamlined process, we're going to keep the Q&A session after the presentation. And during the Q&A session, if you have any questions or comments, feel free to type it in the chat box, or you can use the raise hand function within the Zoom. And I'm providing the project webpage here. We have already posted the final report of the project, as well as the presentation slides for today. And after the seminar, sometime after the seminar, we will be posting the seminar recording. And after the seminar, you can always reach out to me if you have any questions or comments. Now, I'd like to introduce our speaker, Mr. Alan Stannard. Mr. Stannard is a staff engineer at Eastern Research Group, or ERG. His focus is on in-use vehicle and engine operations and emissions testing from combustion engines and vehicles. He's managed and participated in a variety of projects in these areas. And some of the research projects were used to inform regulatory emissions inventory work, like the U.S. EPA's MOVES model and CARB's MFAC model. Mr. Stannard has been a frequent speaker at CRC Real-World Emissions Workshop, and he has published multiple technical articles. So without further ado, let's welcome Mr. Alan Stannard. Alan, I believe you are able to share from your screen.
Yes. Yes, I just requested from Akju to have me share. Okay, great. Tao, could you verify you can see my presentation?
Yes.
Okay, great. Well, welcome everybody to our project seminar for remote sensing measurements of light-duty vehicle emissions at multiple California locations. And this is work that ERG performed for CARB in the Bureau of Automotive Repair, along with the University of Denver and Opus Inspection. So yeah, we want to acknowledge the project sponsors. CARB, as Tao said, it was project 20RD001, and the Bureau of Automotive Repair project participated in the project also and contributed funds to the research. We want to thank various entities for their support. CARB, the staff we worked with was Tao, Sanju Yoon, and Chris Rule. At Denver University, we worked with Dr. Gary Bishop. And at Opus, we work with Naranjan Vesio and his whole RSD team. We also want to acknowledge the Coordinating Research Council, CRC, for contribution to this project that we'll discuss soon. Okay, so in this seminar, we'll talk about the project background, our research goals, and we'll define some of the community types that kind of feed into those goals. We'll talk about the RSD measurement principle, and then the campaigns we had in this work and how we dealt with the RSD data, and we'll talk about our analysis. So we'll go over the kind of the immediate findings of our work, and then our data review from each measurement campaign, and then we'll dive into the analysis supporting our different research topics. Okay, so our research goals for this work were a part of continuing CARB's long-term efforts to measure and analyze pollutant emissions by a remote sensing device, RSD. So that is research that CARB has been conducting and sponsoring for multiple decades now. So we wanted to continue those efforts, but we had specific goals, 6 specific research goals for this work. We wanted to investigate emissions disparities between light-duty vehicles, which you'll see abbreviated LDVs, registered in disadvantaged and non-disadvantaged communities. Another goal will be to continue the historical West LA RSD measurements that have been taking place over multiple decades now. We wanted to review, compare and contrast the emissions rates of in-state versus cross-border vehicles in Southern California. We wanted to evaluate disadvantaged community in non-DAC electric vehicle fractions that we observe operating on the road. We also wanted to look and see what we could use RSD for in terms of analyzing heavy-duty vehicle emissions, which is a little more novel use of RSD in this type of work. And then finally, we wanted to see what RSD could tell us about the Smog Check Program by comparing RSD findings with the Smog Check records. Okay, well, so we'll start with the definition of disadvantaged communities in this work. These have to do with state government, state bill and legislative definitions. So initiating with Senate Bill 535 from 2012. So that bill was more far-reaching than what we'll discuss here. We'll just focus on how it relates to this work. But includes funding for area quality investment to improve the public health, quality of life, and economic opportunities for disadvantaged communities. So what that ended up resulting in was the development of the CalEnviroScreen tool. So this is a software tool that was created to basically assign geographically pollutant, health, or environmental vulnerability as a score by individual census tracts throughout the state. So that California EPA designates which communities are disadvantaged using that tool. Now, most recently, Assembly Bill 617 directs the CARB board to select specific communities for air quality improvements, and it has requirements for tracking progress in air quality improvement over time. So in this project, we'll talk about, we'll sometimes isolate the vehicles that are registered in those smaller, relatively small communities, AB 617 identified communities, and where possible, we'll analyze those as a separate group if we have enough data and measurements. So talking a little bit more about the CalEnviroScreen tool, this is a snapshot of it that shows kind of the level of resolution when we talk about the census tracts that it zooms down into. So this is assigning a CalEnviroScreen score based to each of these census tracts. Again, based on the relative percentiles of pollutant exposure or health or economic vulnerabilities. So in this project, we have assigned the top 25th percentiles of CalEnviroScreen as disadvantaged communities. And so that definition, depending on the different entities doing the research and things like that, that definition could change somewhat. But in this work, that was one of the most original definitions from SB 535. So for this work, we're going to stick with that. So basically, when you say if a vehicle is defined as registered in a disadvantaged community in this work, that means it is a community from which, or that has the top 25th percentile score on CalEnviroScreen. Okay, so we had ERG had two subcontractors in this work. Denver University said they've been doing RSD measurements since the 90s, using a tool or instrument called the FEAT, the Fuel Efficiency Automobile Test, and that was developed and patented originally by Dr. Seddon, and then Dr. Gary Bishop has been continuing the work with that in this project. And then also, given that Dr. Bishop is retired recently, and in fact, this was the last RSD project that he worked on before retiring, we are also working with Opus. We worked with Opus in this work. So Opus acquired the EnviroTest group a number of years ago, and that team had decades of experience with similar measurements as the DU team. So let's talk about the RSD measurement system and device. And so here's an example picture of the RSD setup on an on-ramp to measure a single lane of traffic. So we see the van in the background. So that is the support van that has a generator. In both of our subcontractors would keep personnel on site. And so, but the RSD instruments themselves, this is an Opus setup. There's two systems together measuring in parallel here. So they're measuring across the lane of traffic. So a beam emitter is on one side, and then is the light beam is then collected after scanning the lane of traffic. We also have a laser set up nearby so that we can measure vehicles' speed and acceleration as they're passing by. And then finally, not shown in this, just out of frame, is a license plate reader camera to capture a view of every car that goes by. So the RSD system operates by measuring light attenuation at specific wavelengths corresponding to each pollutant in the vehicle's exhaust plume as it passes by. So by non-dispersive infrared NDIR, we measure CO2, CO, and hydrocarbon. And so the DU has long documented this unseen hydrocarbon issue. So in our case, all HC measurements are multiplied by 2 to account for hydrocarbons that this system cannot see. So that is something that they've determined over many years of research, as to get a comparable result to a flame ionization detector, we need a multiplication of 2. And then by UV spectrometry, we can measure NO, NO2, and ammonia. In this project, in this presentation, we'll focus on the NO measurements because Opus was still developing their NO2 measurements during the project. And they did get that completed, but not all of our campaigns included NO2, so we won't focus on that. Okay, so kind of continuing describing how this RSD system works. As the vehicle passes by and the light beam is being sent through the exhaust plume, measurements made over a half a second period at 100 hertz. So we get 50 points of measurement of basically light attenuation at different wavelengths. And so we can compare those to CO2. So in the figure here, we show the CO2 basically intensity is along the x-axis, and then in this example, CO and HC are shown on the Y. And so as the beam disperses, we move from the upper right down to the lower left in time, generally speaking, in this graph. So the kind of the most intense exhaust concentrations are right after the vehicle passes, and then as the plume disperses, both the CO, CO2, and HC, they all disperse at the same rate, and so we can get a slope of the curve of these pollutants against the CO2, and that allows us to present emission rates on the basis of grams of pollutant against kilograms of fuel as kind of a normalized result, because we can't, with RSD, we cannot capture the entire exhaust plume, so we can't see necessarily the total amount of mass in there. It's just a single light being passing through that. But when we can compare each pollutant against CO2, then we can say, on the basis of correcting for fuel burn rate, what is the relative amount of pollutant formation? So then, so after the measurement takes place, after the half-second process, there's an automated and instantaneous validation programmed into both of our contractors' systems. So they validate the reading for how linear that the pollutants are against CO2, the overall signal strength, and then they also evaluate the vehicle speed and acceleration are reasonable values. So at that point, they can reject a vehicle pass as invalid immediately, and then or put it as valid in the data. They also what they call tag edit, where they check the license plate reader and they check that the license plate transcription is correct, and they do that live kind of continuously as the day is going on. After that, after the campaign is over, they provided the data to us at ERG, and then we manually reviewed that data using data analysis tools. And so we would review it for outliers, trends, and things like that. So we conducted a QA review, then again looking for any unexpected trends or any reason that we thought maybe there were issues that our contractors didn't find. Okay, so then next was to go on to our analysis. So because of the nature of this work, we were kind of investigating the vehicles from communities, not just their emissions, but the vehicles themselves. So we wanted to keep passes that had invalid measurements in some of our analyses. So if a vehicle passed that with a invalid reading, but we still wanted to keep that vehicle for our counts, our vehicle counts and distributions of vehicle types, et cetera. So, but we would just drop them from emissions analysis. So then, as I mentioned, all the emission rates will be presented in this project or this presentation on the basis of grams of pollutant per kilogram of fuel burned. So then, in terms of to complete the analysis, we then took all of our license plates that we observed and matched those with the California registration data so that we could get specifics on the vehicles and communities. So in addition to that describes all measurements, but we had some special consideration because we wanted to see what we could do in terms of capturing heavy-duty vehicles with RSD also. So because of the setup that we saw a couple slides ago in the picture, that measures near the roadway surface, which would be too low for a high stack exhaust truck. So for heavy duty measurements, we knew we would only going to get vehicles or heavy duty trucks that had downdraft exhaust. We also kind of unique in this work we took front and rear license plate pictures. So in that case, if a vehicle was towing a trailer, we could still recover the plate and get an identification of the truck. So the way to do that, it was slightly different, but for DU, they had a single RSD system, but just added a second camera to it. For Opus, they used, as we saw in that picture earlier, they added a complete second RSD system. So they had one that was intended to measure light duty vehicles and one that was intended to measure heavy duty vehicles. And for that one, they triggered it on CO2. And so that would increase the likelihood of a successful measurement given that, and I'll talk about this more, but there's a challenge in terms of triggering the measurement of heavy duty vehicles. And we'll get into that more. And so then on our side, we isolated only one of each of those passes for analysis. Okay, so that is a description of kind of how RSD works, and we're getting here and now into our campaigns for this project. So we had each campaign in this project was about 1 week in duration, and so they shut down every night. So it was only basically daylight or kind of longer business hours, but only within daylight. But they kept the systems in operation on weekends and weekdays. So we had basically tried to get contiguous days, including weekends, so that we could isolate any effects there, if there were any. The goal was to get 25,000 measurements in each campaign. In some campaigns, we got much more than that, and some we had somewhat less than that. All of the setups were on highway on-ramps or highway interchanges. So that's kind of the ideal place to do RSD because you can isolate to a single lane without any oncoming traffic, coming in opposite direction, I mean. And then The other advantage is that if you set it up kind of often, these would be rising terrain, and so you would know that the vehicles would be accelerating or kind of on the power in a sense that they wouldn't be idling or deceleration, so we could get a good solid exhaust plume out of them. So in each campaign, in most of them, we just found a single site within those geographic campaigns. But in some, we had two different ones because we weren't sure going in whether they would have adequate traffic counts to get us to our 25,000 goal. So we might start at one and say, let's move to another to improve our traffic counts, a busier location. So in some cases, we have two sites. That isn't really a big part of this work, and kind of that probably won't come up much again. But anyway, we had 9 total campaigns in this work. So eight were conducted, under this contract, this research contract, and then one was a project or a campaign that CRC conducted under their project RW117. And because they had kind of a similar setup and goal, they offered to share that data for us to analyze in this work. So it fit in with what we were doing anyway for 9 total campaigns. To make the RSD analyses work, we need some other supporting data sets. Importantly, the California Registration Extract. That would allow us to merge our measured vehicle emissions by license plate with the vehicle information itself from the registration, the make, model year for the trucks, the GVW class. We could also get the registration currency and the registration expiration date to just check whether the vehicle was currently up to date in its registration. We could also get the Smog Check Program area for our smog check analysis. We would get the geographic information, including the census tract, and that also returned when we did some geographic analysis based on the Latin long of the centroid of those census tracts. But more importantly, for that geographic information allowed us to get this Calvin Viroscreen score and percentile. And then separately, so that would give us the disadvantaged community status, but then we would also specifically get whether that registration was within an AB 617 community. So those are 2 separate additional sources of information. So all that's the registration extract. Next, we moved to we received smog check data from the Bureau of Automotive Repair. So that gave us data at a by inspection level, such as the data inspection, the vehicle information, just to make sure we've got a good match, the emissions test type and the reason for it, and then the emissions test results and the overall test results from each smog check inspection that the vehicle may have been a part of. And then additionally, for our cross-border analysis, we also had Mexican vehicle registration information. So from different states and localities, from a past project that ERG had done in that area, we had some registration data from those entities from the Baja area. And so that gave us some limited vehicle information for the cross-border vehicles. Okay, so talking about our locations, where did we have our campaigns? So moving from northwest down to southeast, our campaigns were at Oakland, Stockton, and Fresno. Fresno was the site that was provided from or cooperatively from CRC. Bakersfield, West LA, City of Industry, Riverside, San Ysidro, and El Centro. So San Ysidro and El Centro were our near border sites for those analyses. In this graphic here, we're showing also the AB 617 communities that these were in place around the time of this project, over when the data was collected. And so in a lot of cases, you can clearly see we intentionally set up near an AB 617 community so that we could observe and measure some of those vehicles, but not in all cases. Okay, this table shows some campaign findings that are specifics on our campaign. So these campaigns took place from as I mentioned, approximate week-long campaigns in 2021, 22, and 23. And then you can see in in most cases, we had something like 20 to 30,000 passes, but the City of Industry was a very busy site, so we had 56,000 readable passes. And then Fresno was a bit shorter. That was the CRC project, so their intended duration was a bit shorter, so we only had 8,700 passes there. Okay, moving on to our counts and how they matched with the California registration. So these tables start the column on the left shows just the number of scans in which we could read the plate. The next column is the percent that matched with registration. So you can see it depends heavily by the different campaigns, but in some campaigns we had a almost high 90% match rate with registration. Some of the lower ones are the two near border locations, and so it's very likely that vehicles coming across the border were a cause of the lower match rates, where we saw only about 75 to 80% match rates there. Going over, so then the next step was to see how well did we get a matching Cal EnviroScreen score with those vehicles, such that we could then assign their community status. And those numbers are a bit lower, approximately maybe 10% lower. We lose about 10% of the vehicles when we then match with Cal EnviroScreen. So we weren't exactly able to be sure why we didn't get a match for any given vehicle, but in a lot of cases it would be where the vehicle was registered in California, but its mailing address was out of state, or if it was on a PO box, if that was possible, if it was basically a non-residential location, then they would not assign a Cal EnviroScreen. So that was some of the reasons why we might not get quite as high a match rate. But in general, the vast majority of these were matching with Cal EnviroScreen. So by talking about our different legislated community types here, we've got our disadvantaged communities as from SB 535, and then we've got the AB 617 community status, and there's different permutations of a vehicle could be registered in different combinations of that, and this graph attempts to show how that varies over the different campaigns. So the dark blue would be where it's not in either community type. It's not a disadvantaged, and it's not from AB 617. And so that's kind of the dark blue here on the bottom, the kind of the baseline situation. But you can see that despite only the DACs being only the top 25th percentile, we intentionally got a relatively large number, that much more than 25% for a lot of these locations. And you can see that the least common would be if you're not in an SB 535 community, but you are in a 617 community. So for a lot of these, that was exceptionally rare for a lot of the locations, other than El Centro, which has a relatively large AB 617 community. This just the idea here is to show that we're getting a large number of basically not of disadvantaged communities for a lot of these campaigns, and given how small and individual the AB 617 communities are, a lot of these campaigns we did see a number of those vehicles also, as shown by this kind of copper color. Okay, so when we talk about emissions, it's really important to put it in the context of the model years of the vehicles. We know that as vehicles get newer and newer, their new vehicle certification emission standards get lower and lower. We know as they age, they tend to deteriorate in terms of their emissions controls, and they will end up with higher emissions as they age, typically. So it's important to keep that in mind as we understand the emissions. So first, let's just look at the model years of what we saw here. So we'll compare here what we observed in our RSD project, and then we'll look at what's in the registration. So from non-disadvantaged communities, our average model year that we observed on the road was 2013.5, 2013.5. And then from disadvantaged communities, 2012.9. So not a huge difference in terms of the mean there between the two communities, but there was a difference. if we compare that to California registration, we see that the average was 2012 for non-disadvantaged vehicles, community vehicles, and then 2011 for DAC vehicles. So immediately we see some differences here. The vehicles we observed by RSVD tended to be newer than if we just took all the vehicles registered in California, and that is consistent with past research where the older a vehicle gets, the less likely it is to be driven, and the less miles per year it's driven. So the older vehicles will be less likely to see with RSD. They tend to be more parked more often for various reasons. So then we've got these different the actual distributions of model years here. And the dashed lines are the California registration, and then the solid lines are our observed RSD data. So we can see we get these kind of bumps in the non-disadvantaged newer vehicles here in the upper right. And then likewise, they're just it's less common to see them older than 2010. So just wanted to contextualize this and say, this is what we observed, especially as compared to the registration, because we need to remember that the RSD is more likely to see vehicles that are more often driven, which makes it a useful tool. Just on average, to see how the model year varies across the different campaigns. This is the level of variance in terms of average model year. So in every case here, we can see that the disadvantaged community vehicles are older than the non-disadvantaged community vehicles. The error bars here are 95% confidence intervals, so we can establish statistical significance if they don't overlap. So this is confounded. It's important to remember that this is confounded by the fact that it was a 2-year range of this whole project covered 2 years, right? So the campaigns that took place the farthest in the past will tend to have the oldest vehicles, and that we can see that. Fresno was the first campaign done by CRC before this project even started. So, well, maybe about the time this project was starting. And so we observed the oldest vehicles. And then, like, for example, the Riverside and El Centro were more recent projects that we saw. So it's important to remember there's a slight confounding of the model years versus the ages. And in the report, we went into that difference between age and model year, but that's probably more detail than we need for this seminar. So we'll just focus on the model year in this work, but just keep in mind that there is a 2-year delta across these campaigns. So moving on, so going into the observed fuel types we saw for light duty vehicles on the road across these community types. So almost all the vehicles for light duty vehicles were gasoline powered. So we just cut the graph off here below 88%. So in the non-disadvantaged communities, we generally see the other fuel types as given in the registration. This is all from the registration, not from any data that we took ourselves. This is just from matching our observed vehicles to the registration. So we see, more hybrids and more diesel light duty vehicles, and then more electric vehicles in the non-disadvantaged community. And then in the disadvantaged community, more of those vehicles tend to be gasoline, more the conventional vehicle choice. All right, so getting into the emission rates across the different campaigns. So here we'll present HC, NO, and CO. Where these are all presented together, we'll have HC and NO on the left axis and then CO on the right axis. The CO tends to be about 10 times higher, approximately, on average. And so immediately looking at this, you can see we observe a pretty wide range of variability across the different campaigns. And so that is something that is worth noting and discussing further. And maybe the biggest thing to start out by noticing. So we kind of want to, in general, do our analysis on an individual campaign basis, which is more the intention of RSD. So kind of we did some research into this cross-campaign variability during the work. And so we did a number of analyses to try to understand the cause of that. And remember, the RSD, like I mentioned earlier, is taking a half-second snapshot of emissions. And so if you imagine the emission rate throughout a trip, and then you pick a half second out of that, it's that the representation of the whole trip is not the strength of RSD. The strength of RSD is to observe thousands and thousands of vehicles in a snapshot measurement. It's not really intended to extremely well categorize a single vehicle, right? The power of RSD is to measure thousands of vehicles. And so that is kind of a thing to remember when we talk about this. So we did some analysis to try to understand this variability. One thing to note is that within a given site, the day-to-day, like if we compared the 7, say, week of data, the day-to-day variability at a site was much lower than the variability we saw comparing across different campaigns. Each campaign or each location is a little bit different in terms of how the vehicle will be operating. The vehicle will be accelerating with a lot of power. Some it will be more like cruising, kind of at an interchange. So we can estimate vehicle-specific power using the speed and acceleration. So that's what we're saying there by VSP. We can estimate the power level based on the vehicle and acceleration. And we did see that they have those differences have a minor measurable effect, but they didn't explain the whole measurability. Weather did not appear to affect it. Each of the systems logs some temperature data, and we also had almanac data for the nearby weather stations for every day too, that we compared to just to determine a weather effect. We did not find a weather effect. Another thing we did is what we called the narrow spectrum analysis. And in that case, we would isolate to we would take the range of data we were collecting and the information we had about a given RSD pass and isolate down to a narrow range and see how much variability. For example, if we had vehicles ranging from a 1990 model year to a 2020 model year, we might take a 2003, 4, and 5 and say, take only those vehicles. And we might have vehicles from disadvantaged communities and non, and say, well, just pick one and take that. And just keep narrowing down, isolating on every factor that we had to analyze by, and just get it boiled down to all the causes, like the Smog Check Program area, and just say, get rid of all of the different sources of variability that we know of within RSD data. And interestingly, we found that did not make a huge improvement in our variability across campaigns by doing that. So that was interesting. So that made us realize that the RSD data probably cannot explain this. So we went out to other projects that ERG has been involved with for RSD projects, and we did see a similar levels of site-to-site variation. And it's very likely that just the exact vehicle operational characteristics of a given site affect the emissions to some extent. So the take home was we want to really, where we can, analyze across these different subjects within a given RSD campaign, not so much cross-campaign comparisons. So let's get into the first research topic, which was to try to better understand the emissions characteristics of disadvantaged community vehicles versus the other vehicles. And so here we have hydrocarbon emission rates by the different community types and by across the different campaigns. So in this case, on the left is the non-disadvantaged vehicles. The central within each group, the central is the non-617 community, but otherwise SB 535 disadvantaged community vehicles. And then on the right is any vehicle that was registered in an AB 617 community. So where we have enough data, such as at this level, we can separate out the two different community types of interest. And in this case, you can see that in most cases the emissions are higher for the disadvantaged community vehicles. Not in all cases. In almost every case, one of the two will be higher, but you can see our 95% confidence interval bars are fairly large compared to some of the differences. In others, the differences are larger. So the emission rates are higher, but in this case, it's not always, many of the campaigns, it's not significantly significant. So statistically significant, excuse me. So that's hydrocarbon. Moving on to CO, we get a little more of a consistent trend here. In almost all of these cases, we see that the disadvantaged community vehicles are higher in emission rates of CO. And in some of them, Oakland, for example, would see a statistically significant difference. Bakersfield, we see one here, City of Industry. So in more and more of these campaigns, we're starting to see significant differences in terms of CO. So let's go on to NO. So in this case, maybe it's not quite as clear a trend as CO, but more so than HC, that a lot of these either of the disadvantaged community types or both are statistically higher in terms of NO emission rates. Fresno being a notable exception, in which case the trend is reversed. But in most of these cases, we can see one or both of those communities have higher emission rates. So we've already talked about the effect of that we expect older vehicles to have higher emission rates, and we've observed that the disadvantaged community vehicles do tend to be a bit older. So can we try to understand the effect of that difference in age, or is there a difference that's not explained by age? And so we can also do this comparison by model year. Again, these are 95% confidence interval bars here for and because of the size of those, we're just going to isolate this analysis down to non-disadvantaged and SB 535 disadvantaged communities. So as we starting on the right is kind of the newer vehicles. The newer vehicles, the differences tend to be fairly small, and as the vehicles age, this is where we start to see bigger and bigger differences in terms of the emission rates. And including starting in about 2011 here, we start to see statistically significant higher emission rates for the disadvantaged community vehicles. In a couple of these model years, we see it here in 2011, in 2004, and then 2001. So we start to see these trends in most of these, the average is higher, and in a couple of these, it's statistically significantly higher. So that's making the community types equal in terms of model years of the vehicles. We still see statistically significant elevated emissions from the DAC vehicles. So that was HC. Moving on to CO. In this case, we start to see a lot of where the mean for the disadvantaged communities is higher, but fewer that it's statistically significant. 2001, and interestingly, the reverse is the case here in 2018. So just a little more noise in this analysis for CO, a little less conclusive than it was for HC. And then going into the NO, kind of interestingly, the NO emission rates are very similar for the two community types, getting older and older from 2022 back to about 2010. As vehicles get to be about 12 years old, that's where we start to see a difference in emission rates, and they start to become statistically significant. We see one year here, 2006, where they are, and then generally a lot more noise here, like much larger error bars here, where we see a non-statistically significant difference of where the non-disadvantaged vehicle is higher. So again, it's what we don't necessarily see that the two community types just completely diverge, and it's obvious, but we do see where we just start to see the trend that the data shows us that in a lot of these model years, the disadvantaged community vehicles have elevated emission rates, irrespective of their model year. Okay, so just to review, the non-disadvantaged community vehicles tend to, I think I've got a typo here. Sorry, apologies. The disadvantaged communities tend to be older, and then so that is a partial explanation of the exhaust emission rate differences. but not a complete difference, right? The differences we see persist even within given model years. So we can try to estimate the fraction of those elevated emissions that are not caused by the model year difference. So what we could do is say we could find the overall, we could try to recreate the non-disadvantaged emission rates by reweighting their emission rates to the disadvantaged community model year distribution. And then if we do that, we find that maybe a third to a half of the emissions are not caused by the model year difference. So maybe just a little, you could say a little less than half of the emissions are not caused by the model year difference. And then so maybe a little more than half. The model year difference explains maybe a little more than half. This is a pretty gross estimate here of what they are for each pollutant as kind of a percentage of the difference explained. Okay, so we'll move on to the next research topic here, which was the historical West LA data. Okay, so this is at the La Brea Avenue site where Dr. Bishop and DU and Dr. Stedman had been making measurements all the way back to the 90s at the on-ramp from La Brea to I-10. So this is using that historical data from DU in the addition of our campaign, which took place in 2021. And so adding it to this. So this is on average the emission rates of the three pollutants that they've been observing and throughout this period of time. And so we can see a relatively steady decline in average emission rates up until about 2017. And in our data, the NO is continuing to decline at almost this exact same rate as it has been the last couple of times that they've been. They go about every 3 years here, as you can see. But the HC had leveled off two campaigns ago and is continuing this slight uptrend. And then the CO is kind of leveled off and has a very slight uptrend here. So the NO is continuing to decline on average, but the HC and CO have leveled off. So it'll be interesting to see as time moves on if we can continue to conduct this research, whether these trends continue. I thought it would also be interesting to look at the kind of the high emitter share of the emissions. So this is the percentage of emissions from the top 1% highest emitters across the measurement years from La Brea, the West LA site. So the most monotonic is the NO. So the emissions share of the top 1% of emitters has gone from 10%. The top 1% of emitters has gone from 10% back in 99 all the way up to almost 35% now. So most vehicles are getting clean. The way to think about that would be most vehicles are getting cleaner and the dirtiest ones are taking a higher share of those emissions. But it's very likely that I'm sorry, what we saw in the previous slide is that the total emissions are coming down despite this, or probably caused by this. But then the trends for HC and CO are a little less consistent. And because we've seen with that tailing up on the emission rates, that's actually caused the share of the highest emitters to come down over the last couple of years, interestingly. Okay, moving on to the cross-border campaign research topic. So this is we're gonna look only at the El Centro and San Isidro campaigns. So for El Centro, the RSD campaign sites, we had two sites, basically opposite on-ramps at the same intersection. They were approximately 8 miles from the border. And of the vehicles we saw, approximately 6% of the readable plates were ID'd and matched our registration data from Mexico. And then just comparing that with San Isidro, we also had two campaign sites. They were much closer, approximately 1 and 3 miles from the border, respectively. And then there we saw approximately 9% of the readable plates matching our Mexican registration. So our contractors would note the country or state of origin where possible. So we have the stat here: approximately 77% of our readable Mexican license plates, i.e., they identified them from as being from Mexico, they matched with the registration data that we had. So what we saw was all of those were light duty vehicles, and despite our registration data including some heavy duty vehicles. So we had actually enjoyed a surprisingly high match rate, we found, despite not necessarily having a formal set of registration data made specifically for this project. Okay, so as we did before, let's review the model years first so that we can put the emissions into context. So the table here shows the mean model years. So for El Centro, the mean California fleet, i.e. vehicles matching with the California registration, was 2014.8, and then the average Mexican fleet model year was 2015.1. So really very close at El Centro, surprisingly so to those of us when we were first doing the analysis. San Isidro, the difference was just a little bit larger. Average model year from California, 2013.2, and from Mexico, 2011.5. So a little bit more of a difference there. And then here are the different combinations in terms of the model year distribution. So some noise, both vehicle fleets kind of showing the decline in sales from the financial crisis. But then in general, the El Centro vehicles newer, but not too different, except in San Isidro here we see just there's this kind of this let's see here, like this San Isidro being the round dots. So we kind of see a lot of noise here, but on average, the San Isidro vehicles are older, but the U.S. vehicles from San Isidro are newer. So hopefully not belaboring that too much. The take-home being that they're not that different in model year. Okay, so let's go into the average emission rates for our three pollutants that we're focusing on here. So on the HC and NO are going to be on the left axis and CO is on the right axis. So for HC, we didn't see a lot of difference across the different community types. Again, the blue is the U.S. vehicles, El Centro at the left, San Isidro the next. And then the green vehicles are the vehicles from Mexico, El Centro on the left and San Isidro on the right. So for HC, we don't see a huge difference, but then we see very pronounced differences in NO and CO. So statistically significant differences in the fleets by country of origin, despite their similar model years. And so that kind of jumps out for NO and CO. If we analyze it just by model year, we can see kind of we kind of see a similar trend as we saw with the in the other by model year analyses. Their vehicles are fairly similar when new, and then we start to see more of a divergence for the older model year vehicles. So that's what's driving the difference for this is hydrocarbon. Many model years where we have statistically significant differences. CO, again, more of a difference throughout, but we can see it diverges in the older model years. A lot more noise for CO than HC. And then NO will be last here. And we can see that divergence seems to happen a little more in newer model years. So we see that divergence happening about 2015, and in almost all of these model years, there's statistically significant differences. So just thinking about this kind of in summary, what we see is that overall the model years were not that different between the U.S. registered vehicles and the Mexico registered vehicles, but the Mexico registration vehicles had a much higher emission rates. This is likely due to their certification standards, in part. Generally, their certification standards correspond to maybe 10-year older kind of where the U.S. was 10 years previously, approximately. But we also see that a divergence in the older model years, which is partly due to the certification standards applicable at that time, but it may also be partly due to the Smog Check Program, and there not being necessarily an equivalent of one in Mexico. Um, so moving on to our next research topic, which was the electric vehicle fraction, and then kind of by community type. So a little note here to kind of remind ourselves that the non-disadvantaged fleet overall across the whole project was about 1% EV, and then the disadvantaged community fleet was about 0.3% EV. But immediately you notice that, unsurprisingly, that this varies widely by the campaign location. So Oakland had the highest prevalence of EVs, with West LA being next. And you can see kind of the non-disadvantaged was at the highest prevalence, at a little over 3.5% of the observed vehicles, and then less or so for the 617 and disadvantaged community vehicles. And then as we go to some of the sites such as Riverside, El Centro, San Isidro, kind of very few EVs observed in those locations. Thought it would also be interesting to show the model year distributions of what we observed, and in that case, we didn't really see much difference between the disadvantaged and non-disadvantaged community in terms of. So if we isolate down to only the EVs within these two communities types, and then show the model year distribution, they really fall right on top of each other. So because of probably this is kind of the speculation about how to explain this, is because this is a relatively new technology and there's not that many older vehicles, that the community type isn't really selecting so much. Like if they're going to select an EV, they would be selecting from the same pool irrespective of community type, and that the newer vehicles are just so much more prevalent on the market. So we don't see much divergence in the model year distributions here for EVs. So going on to the heavy duty analysis topic. So as I mentioned, it's a little more novel to use RSD for heavy duty measurement for an on-road program such as this, where we're measuring at on-ramps. And that's because it's just quite a bit more challenging. And we saw a lot fewer valid measurements of vehicles that we identified as heavy duty. So as I mentioned, we could only detect downdraft vehicles only. So vehicles that had their exhaust stacks high, we would be valid measurements. But there's also to think about, this is a light beam based system. And so if a vehicle's towing a trailer with chains, or they have large mud flaps, or different types of vocational equipment, we have all these different objects that can interrupt the light beam and confound the RSD measurement. So all of those things can help participate in reducing our likelihood of successful measurement. And so in terms of the valid measurements, we see up to 30 percentage points less than our LDV valid measurement rate. So unsurprisingly, the class 3s we're showing the percent valid measurements by truck class here. The class 3s, which look and are designed most like light duty vehicles, had the highest prevalence at 60% valid. And then down in the 6s, 7s, and 8s, we see less than 20% of our measurements were valid. So we take the fact that there are fewer HDVs on the road than there are LDVs, and then we confound that with the fact that we have far fewer valid measurements of each, that it becomes a lot harder to conduct statistical analysis on the heavy duty vehicles. But we can make observations of what we observed, even if the valid measurements, irrespective of whether the measurements were valid or not. So this is kind of the quantity of the different vehicles that we saw by truck class across the different campaigns. So kind of most of what we saw was class 3. Again, they're the most like LDVs, and so are the most prevalent. And then class 7s were the least observed, and it varied somewhat by by campaign site. In some of these cases, our campaign would be set up near maybe a vocational location where a certain type of vehicle would pass by. We saw that a little bit, and that would kind of cause these different spikes for individual campaigns if a given vocation was nearby. But in general, this is what we observed in terms of the distributions of heavy duty vehicles on, operating at our campaign sites. Talking about the fuel types that we observed, the diesel is the bottom in blue here, and that share goes up as we go up in truck type, as we'd expect. So about 50-50 gas versus diesel in the class 3. A little more gasoline in class 4, and then we start to see the dominance in the diesel market share as we go higher. And we started to actually see some natural gas vehicles show up as identified by the registration data. Let's see here. So this gets down to our actual emission measurements that we made. And you can immediately see the size of the error bars here because of the reasons I've already explained. So this is isolating to just city of industry, because that was the location that had the highest rate of valid HDV measurements. So that's why we're going to focus on that. Some of the sites had to the point where we would have almost all of these bins would be empty. We wouldn't even have valid measurements at all for a lot of these. So at least with this site, we could populate a lot of these locations, or these bars here. But as we'd expect, in general, with the newer vehicles, we see a consistent decline in emission rates, and then we do see an increase, kind of a noisy increase in emission rates within each model year group as we go up in truck class. And so those are kind of the take homes from here, and these are the rates of what we saw, and just being careful to note the large error bars. Extremely few measurements, obviously, for the pre-2007s. Just a few got in there somehow that might be exempted, or yeah, we can see very few. We didn't have 7s and 8s, as it's not, they're not legal to operate. So we didn't have 6s and 7s, sorry. And if I could explain, there's no error bar on this class 8 because we only observed 1, because it must have had some exemption or B. I don't know how it was in this set. Okay, so without belaboring the heavy duty vehicle analysis, it's very challenging to measure these vehicles with RSD. So moving on to our final research topic was the smog check analysis. So we had a couple of goals with this to see what light RSD could shed on the smog check program and help give some feedback to that program. So our goals here were to evaluate the emissions of change of ownership area vehicles as compared to the enhanced and basic area vehicles. So I'll explain in a minute of those different program areas. We wanted to compare the unregistered and out-of-state vehicle emissions rates to in-state vehicles. We wanted to look at the RSD emission rates that we observed against the different inspection stations themselves to see if some of the inspection stations might be associated with a higher passing emission rate and maybe, but also higher emissions, just to see if there might be anything observable in terms of a discrepancy from expectations on an individual station basis. We also wanted to determine if any trends existed throughout the 2-year biennial inspection. So do emissions tend to trend in a certain way across during that 2-year period between inspections for the biennial vehicles? And then finally, we wanted to evaluate the effect of the 8 model year exemption for enhanced and basic vehicles and see if RSD could shed any light on that. Okay, so talking about the program areas here, as I mentioned, there's 3 program areas: enhanced, basic, and change of ownership. From the RSD perspective in this analysis, the amount of data we had, the enhanced and basic areas can be treated the same way because of these reasons here. They both require an inspection every 2 years. They require an inspection on change of ownership, and they include an exemption for gasoline vehicles that are less than 8 years old. And that is something that the 2 programs have in common and is relevant to our analysis. Alternatively, the change of ownership area, which would be like the less inspection intense area, requires an inspection on change of ownership only. There's no biennial requirement. And so this is a map of the areas, the inspection areas as of 2018, with our campaign sites here in the red dots here. So you can see 8 out of our 9 inspection areas are deeply within the biennial areas in green, and in almost every case they're within the enhanced area that also. So as a result, only the El Centro was outside of it was in the change of ownership area, and all of the others were really not even particularly close to the change of ownership area in a lot of cases. So that's going to be something that's going to be a confounding factor to our analysis here. So when we talk about this analysis was heavily confounded by these facts here, is that there's a significant overlap in the disadvantaged communities and the change of ownership communities, especially here in El Centro, where that they largely overlap completely, and that the El Centro was the only campaign we had which was in a change of ownership area for comparison. So it turned out to be really the only campaign where we could make meaningful analyses on some of our goals here. So starting off with matching, how well did our data match the smog check records that the Bureau of Automotive Repair provided us? And again, just to remind, that was data based by vehicle visits for an inspection. So we would get a plate and then the events that took place in that inspection and the results. So how well do these match? Do the vehicles that we matched with California registration? How often did we see them in the smog check data we had? And so obviously, because of the 8-year exemption, we want to separate this into the 8-year-old groups also. So if we isolate to only the 8 model year exemptions, we see about 90% match with the smog check, as in those vehicles did go and get a smog check and appeared there and matched by their license plate. If we take all model years into consideration, it's much less because of the exemption. More than half of these vehicles would have never had a change of ownership, so they would have never had reason to go get an inspection. So they don't appear in the smog check records. Obviously, for El Centro, the numbers are much, much less because the vehicles that are based in that location are not required. They're in a change of ownership area. So they would be much less likely to have visited an inspection and only happening on a change of ownership or having driven through from a different location. Okay, so continuing on kind of saying, what is the program area assigned to each vehicle that we observed in our RSD data? And so the enhanced area is this kind of lighter blue here, and you can see for most of the sites, 90-ish% of the vehicles were based in an enhanced area, and then this kind of orange color is the basic area. So our biennial vehicle groups are the large light blue, and then the copper. Now there's this assignment of partial. That means that based on the census tract it contains both. It's like on a border. So some of the vehicles may be required to be a part of it. Some of them may not. It's just that the requirements, they're not on the same basis, so that there's not a hard line in our data between the two. So that's what this dark blue is. And so then you can see for El Centro, a large group of change of ownership area vehicles. So only a little over 10% of our vehicles were from a biennial area. So even here, the direct comparison is somewhat confounded by the fact that it's not really near 50-50 here in terms of making a comparison of these two vehicle types. But because all the others have less than 3% in the change of ownership area, El Centro is the only campaign location that we can really use for smog check analysis. So let's talk about some of the emission rates across these program areas. So again, we're isolating to only El Centro. And let's just talk about the average emission rate by model year group here. So in my note here, I'm just saying that HC didn't show any significant differences, so we'll leave that out. We'll just look at CO and NO. And we can see that in a lot of these, especially for older vehicles, the pre-2001, this change of ownership area vehicles have significantly higher CO and NO emissions than enhanced vehicles. It doesn't apply to every model year group. 2001 to 2005, our error bars are too big to draw significance. But in 2006 and 10, they are significantly different for both CO and NO. And then they are significantly different for NO in the slightly newer vehicles. So we do see a difference in these vehicle types. But again, as I mentioned, this is potentially confounded by the difference by the fact that a lot of the change of ownership areas are also disadvantaged community vehicles as well. So we have multiple potential explanations for this. We also wanted to evaluate the effect of the 8 model year exemption, and that's quite difficult to do with RSD because there's no group of vehicles that are measured in large numbers prior to that would be affected by the Smog Check program. So what am I trying to say there? Let's just dive into it. The vehicle age is on an x-axis, and then the average emission rate on y. Again, as we've seen, and when we do these charts, we see this divergence in time. So in the past by model year charts, we know to expect a divergence as vehicles age. And interestingly, we start to see significant differences right at the 8-year exemption point. And it's likely, we're not involved with this, but it's very likely that that's why the 8 model years was selected, is because that tends to be when vehicles start to have more deterioration. And so we see the change of ownership area vehicles start to become noticeably dirtier at that time. So this doesn't really prove any effect of the 8-year exemption, but it does show that we do start to see a divergence and a rise for the change of ownership area vehicles after the point of 8 years. What we don't know is, would these enhanced area vehicles be lower throughout if it weren't for this exemption? We don't know that. This data can't explain that to us or explain that. So some of our other analyses of the smog check were inconclusive due to the confounding factors that we described, and then for these explanations here. So we wanted to compare the emissions of out-of-state vehicles to in-state vehicles. But without out-of-state registration data, we couldn't conduct anything meaningful because, as we've shown, really all of this emission rate comparison has to be done on a by model year basis, or at least grouped by model year. We also investigated smog check stations to see if they had unusually high passing rates that were associated with high emitting vehicles, but we were not able to isolate any stations based on looking for outliers on that. There were over 6,000 stations visited by the vehicles that were RSD'd, but our total population of RSD measured vehicles in total visited over 6,000 stations. It was just too many stations to make any statistically significant observations, because each station, if we reverse it and say each station we identified only had a couple of vehicles that we RSD'd. And like I mentioned, the benefit of RSD is when you're comparing large numbers of vehicles, not kind of on an individual vehicle basis, because it's such a snapshot. And then we also wanted to look at emissions over the inspection cycle, for enhanced and basic area vehicles. Do we see a trend in emissions over the 2-year inspection cycle? So imagine after an inspection, the vehicle's clean. Does it tend to get dirtier and then kind of clean up at the time of the next inspection? And we did a number of analysis based on kind of the months before and months after and the emission rates. But again, those were inconclusive, largely because of the nature of, then that kind of becomes an individual vehicle analysis, which is really not what RSD is suited for. We really want to be doing large numbers of vehicles in comparison across those large groups, not so much what does an individual vehicle do if it's before or after an RSD, before or after an inspection when measured by RSD. That is a less useful way to use the tool that is RSD. So in summary of the project, we had 9 week-long RSD campaigns throughout the state. We did observe differences for the disadvantaged community vehicle fleets. We saw most of the disadvantaged community vehicles were disproportionately gasoline powered, or more so gasoline powered. We saw that those community vehicles had higher emission rates and older model years, and they had higher emission rates even when adjusted for model year. We continued the historical West LA measurements that have been taking place since the late 90s. We saw the continuing NO emission rates, but the kind of the steadying and slight increase for CO and HC at the average level. In terms of the cross-border findings, we saw that the cross-border vehicles coming across from Mexico had similar model years, but tended to have higher emission rates, especially CO and NO. In terms of the HDVs, we saw that we had much larger error bars around our emissions conclusions there. But as we might expect, the older and larger vehicles are the highest emitters within the HDV measurements that were successful. For the Smog Check program, the change of ownership area vehicles and enhanced vehicles, we saw that they had similar emission rates during their first 8 model years, but then the CO, from there on, when they aged, the COO vehicles tended to have elevated CO and NO emissions. And a lot of our findings with the Smog Check were very limited statistically due to the correlation and confounding with the DAC status and the campaign location. As we kind of discovered the effect of that throughout the program. So in terms of future work, as I was just saying, I think it's important to consider the confounding factors for the location, the location selection. That was primarily driven by our experience with the Smog Check program. Obviously, the more different research goals you want to have met with the program, the more the confounding factors will come into it. If this had been only a Smog Check evaluation, we could have selected locations that might have been where we might have gotten 50% in each area and then be able to control for other factors. But when we have multiple goals in this work, and it was hard to pick the perfect locations for all. We would recommend the continuation of the historical West LA data. That's a really unique and useful data set that shows the change in the fleet emission rates throughout time at the exact same location. I believe that RSD is a useful tool in evaluating certain AB 617 programs to see how the emission rates of vehicles based on those locations changes with time. We would want to revisit the approach to heavy-duty vehicle sampling. Would we have better success if we had directed our system specifically for high stack exhaust? And also think about, like I was mentioning, what the benefit of the RSD is comparing comparing trends across large groups of vehicles. So what would be useful A to B comparisons? Like for the light duty, we had the disadvantaged community versus non-disadvantaged community. And we had in a lot of campaigns, 50-50 kind of roughly counts of vehicles from those two locations. So that was a good A to B comparison. We could think of what would be a useful A to B comparison that we could do within the heavy duty vehicle range. But we would need large counts to bring those error bars sizes down. And then another going back to the variability across campaigns within the light duty vehicle is ways to prepare for that. One thought would be to maybe separate the RSD to do 2 RSD instruments maybe in series, but separated by a longer distance to see how much does the emission rate change over kind of a moderate distance at the exact same site otherwise. So that would be one way to think about that. One thing that would drastically increase the statistical power of the RSD analyses would be if we could bring all different separate campaigns together and analyze them as one. It probably isn't possible, but if we could, that would allow for a lot more statistical power. So I just want to say here that portions of this work were presented at the 33rd CRC Real World Emissions Workshop also back in 2023. Some of that was presented there originally. So I just want to share that. And then also I have my contact information if you'd like to be in touch. And with that, we'll conclude.
Thanks, Alan, for the presentation. We have a question in the chat from Andrew Burnett. This is for slide 19. Alan, if you could go back to 19.
Oh, okay. Oh, here?
Right. So Andrew's question was, how can you tell whether a vehicle not registered in California is DAC or non-DAC?
Oh, we can't. Oh, yes. And so maybe there's something about this that's misleading, right? I don't mean, yeah, maybe this was a little misleading. When I say all observed RSD with a model year, that is all observed and registration matching RSD, and that's where we got the model year. So yes, good question. If it didn't registration match, we wouldn't have known the model year. So yes, all the analysis for which we had model years for California vehicles, those are all isolated only to those that match with registration in California.
Yeah, so my understanding is this. Let me know, Alan, if this is accurate. So the all observed RSD, that is the sample from the study. And the CA, the California registration, that refers to the vehicle population in the DMV database.
Yes.
Millions of vehicles.
Yes, all 40 odd million, yes.
Thanks. I see two more questions. One from Pamela Keeney. Are the DAC communities urban areas with industry, business, more traffic, etc.?
Yeah, not necessarily. And you're welcome. Cal Enviroscreen is a public tool, so you can go on there and review. It's a nice tool in terms of the graphical map. You can go through and look yourself and see anywhere you want to see in the state, or zoom out and see the whole state. But it's attempting to create kind of health vulnerability across a variety of metrics, right? So yes, areas with a lot of industry or traffic will be on there, but a lot of the very rural inland parts of the state that do not have that are also on there because they have vulnerabilities caused from other sources. So yes, I that's an attempt to answer that question as best I can, but it is a public tool, and you can go and see and review it and use it and look across the whole state on your own. Yeah.
Okay, thanks. Another question from Rebecca Simpson. Will the data be available?
Yeah, why don't you?
Yeah, so we intend to make the data available to the public. And please follow along the project website for more updates in the future. And I posted the URL link in the chat, a few messages above. Another question from Rebecca. Did you look at emission rates by time of the day?
That wasn't really a priority. We were just looking at kind of the averages throughout. That might be interesting, but I don't think that was something we did really fundamentally for our research topics. But that is something that data could be mined for in the future. There's a lot of other ways the data could be mined to get more specific. Yeah, we could also see the traffic counts, and we did look at we were analyzing for the VSP, the vehicle specific power, and so we could see that would change throughout the day for certain locations. As we were trying to, we looked at that primarily for the purpose of explaining the variability across the campaigns and trying to see was that a part of it. So that was really the only thing we looked at in terms of trends throughout the day.
Okay, thanks. Another question from Rebecca. Why did you choose average as your main statistic?
Yeah, that's an interesting question. I think it's the best way to say it would be that we were trying to get a snapshot of the total emissions as they affected air quality, right? And so then that total would just be on a basis of total emissions divided by the vehicle, each vehicle, total emissions by total vehicles. So that would be the average. Yeah, in only one analysis did we try to isolate the highest emitters. But I think we were just trying to say, in terms of the total effect on air quality, the average would be most correlated with that.
Okay, thanks. Are there additional questions or comments? If not, I think we can conclude the seminar. Thanks, Alan, for the presentation, and thanks everyone for participating.
Yes, thanks everyone for joining, and thank you, Tao.
Thank you.